Okay, let's unpack this. Imagine a fundamental building block in modern neural networks. Something so common, so universally adopted, we pretty much take it for granted. But what if it turns out we might not actually need it? What if there's a remarkably simple technique that gets you the same, maybe even better performance without it? Today, we're taking a deep dive into a really groundbreaking paper. It's titled Transformers Without Normalization by Jiachen, Xinlei Chen, Kaiming, Yann, LeCun, and Zhuang. And this work, it challenges, well, pretty much a decade of conventional wisdom about normalization layers in deep learning.
Indeed. And our mission for this deep dive is to professionally and comprehensively break down the core concepts, the really innovative ideas, and of course, the empirical results they present. We'll explore how they manage to get state-of-the-art performance in all sorts of transformer architectures, vision, language models, without the normalization layers we've all come to rely on.
So if you're deep in the weeds of machine learning, data science, advanced math, get ready. This could genuinely shift how you think about network design and training. Let's get right into it. All right, so first off, normalization layers, they're everywhere, right? Especially in deep networks, it feels like you just can't build a modern network without them.
That's exactly the prevailing view. And it really kicked off back in 2015 with batch normalization, BN, from Ioffe and Segedi. That paper was, well, pivotal. Before BN, training really deep networks was notoriously tricky. Unstable, gradients vanishing or exploding. BN was a game changer for speeding up and stabilizing convergence, especially in vision.
Right, it made things possible that were just too hard before.
Absolutely. And its success led to a whole zoo of variants like group normalization, instance normalization, each tackling specific issues like maybe small batch sizes or certain tasks. But for transformers, the architecture that dominates so much of ML today, two types really stand out. Layer normalization, LN, and root mean square normalization, or RMS norm. LN is probably the most common. It's simple, works independently of the batch size, great for sequences. You find it almost everywhere. RMS norm, though, it's gained a lot of traction, particularly in LLMs. Big names like T5, Alama, Mistral, DeepSeek, they all use RMS norm.
And it really shows how indispensable people think they are. I mean, researchers swap out attention heads, change FFNs, but the normalization layers, they almost always stay. It's like this foundational piece you just don't touch, especially as models get bigger and deeper.
Exactly. So to really get what this paper is challenging, it helps to quickly look at the general math behind these layers. At their core, they all kind of do a similar thing. Take an input tensor, normalize its statistics, basically recenter and rescale the values, and then apply some learnable parameters.
It's a scaling and shifting bit, right?
Yep.
Gamma and beta.
Precisely. So the general form is something like normalization x. Let's score it's 2 plus co. You've got the input x, a tiny epsilon on for stability, and then those learnable affine parameters, gamma and beta bar. Usually vectors acting per channel. They let the network learn the best scale and shift for the normalized output, rather than forcing it to zero mean unit variance. Gives it flexibility.
Okay, that makes sense. Standardize, then adapt. But you said the key difference is how they get that mean, mu, and variance, sigma squared.
Exactly. That's where they diverge. Let's take batch norm first. BN calculates the mean and variance across the batch dimension and the token or spatial dimensions, but for each channel separately. So for one feature map, it averages over all the samples in your mini batch in all locations. This is why BN is sensitive to batch size. Small batches give noisy stats.
Right. I remember that being a pain point.
Yeah. Now, layer norm, LN, does it completely differently. It computes mean and variance for each token independently across all channels within that token. So for a single sequence element in a single sample, it normalizes across its entire feature vector. That makes it totally independent of the batch size, which is great for transformers and variable sequence lengths.
Much better suited for sequential data.
Definitely. And then there's RMS norm. It's basically a simplified LN. It just skips the mean centering part entirely, assumes mean is 0. It normalizes only by the root mean square of the activations across channels for that token. It's simpler, sometimes a bit faster, and works surprisingly well, especially in many of the big LLMs we mentioned.
So same goal, stabilize activations, but different ways of calculating the stats to do it.
Exactly. The how and where of the statistics calculation is the main difference.
Okay, now here's where it gets really interesting. The paper didn't just propose an alternative. They started by digging into what these normalization layers actually do empirically in trained networks.
Right. They set up a pretty careful analysis. They took trained models of VITB on ImageNet, a large Wave2Vec 2.0 model on LibreSpeech, and a diffusion transformer, DITXL, also on ImageNet.
So vision, speech, image generation, A good spread.
A very good spread, yeah. And the method was meticulous. Sample a mini batch, do a forward pass, and measure the tensors right before and right after the normalization step. Crucially, this was before applying those learnable gamma and beta parameters, just the raw normalization effect.
And because ln outputs the same shape tensor as the input?
They could make these direct input-output plots. Element by element correspondence. Figure 2 in the paper shows this beautifully.
And those plots, they weren't quite what you might expect, were they? Especially deeper in the networks?
Not at all. In the early layers, say layer 5 in their examples, the relationship looks mostly linear, like a straight line, which kind of fits the simple rescaling idea.
Okay, makes sense so far.
But when you look at deeper layers, layer 15, 20, 25 in VIT, 30, 35, 40 in wave QVEC, 13, 21, 28 in DIT, the pattern changes dramatically. You see these really strong S-shaped curves. And what's remarkable is how closely they resemble a tan function, specifically tangs, as they show in figure 3.
Wait, Tan, how does subtracting a mean and dividing by a standard deviation turn into a tan? That seems non-obvious.
It is non-obvious and counterintuitive because, yes, subtracting the mean and dividing by the standard deviation are linear operations. And ln does apply a linear transform to each token's activations independently. But here's the catch. Each token has a different mean and standard deviation. So the linear transformation applied is slightly different for every single token. When you plot all those activation points together, the collective behavior, the ensemble effect, becomes nonlinear, and it looks like 10.
Okay, so it's the aggregation of many different linear transforms that creates the overall nonlinear shape.
Precisely. And this leads to that squashing effect you mentioned. The central part of the S-curve, near 0, is still pretty linear. Most activations fall there, maybe 99% of them. But the extreme values, think activations way out, like 50 or next in 50 in their VIT example, they get disproportionately squashed, pulled back towards the center much more aggressively than the points near 0.
So it tames the outliers.
Exactly. And the paper's central hypothesis is that this nonlinear, disproportional squashing of extreme values is the real indispensable function of normalization layers. It's not just about standardizing. It's about this targeted compression of outliers.
That's a really neat insight, and it ties into other work too, right?
It does. There was recent work by Nye et al. Highlighting ln's nonlinearity actually boosting representational capacity. And maybe stretching a bit, but it even echoes, the saturation in biological neurons when inputs get too strong, something noted way back by Adrian in 1926. A fascinating parallel.
Okay, so the collective effect is nonlinear, but figure 4 breaks it down even further, looking at tokens versus channels. How does that clarify things?
Right, figure 4 gives us that finer granularity. If you look at the left panels, colored by tokens, you see exactly what we discussed. Each token, each color, forms a straight line. Linear transform per token. But critically, different tokens have different variances, so the slopes of those lines are different. Put all those lines together, and boom, you get the overall S-shaped curve.
Got it. Aggregate effect of varying slopes.
Exactly. Now look at the right panels, colored by channels. This shows something else. Different channels have wildly different activation ranges. Some are narrow, near 0, but only a few specific channels actually contain those really large extreme values, the outliers that need squashing. The figure highlights a few in red, green, pink, and it's those channels that get squashed the most by the normalization, contributing heavily to the curved parts of the S-shape. Channels with smaller ranges mostly stay in the linear part.
So it's a combination. Varying linear transforms per token, but the nonlinear squashing is primarily driven by extreme values occurring in just a few specific channels.
You've nailed it. That's the mechanism unpacked.
Okay, so armed with this insight, that the key function seems to be this tanh-like squashing the paper, proposes a replacement. And it's surprisingly simple. Dynamic Tanh, or DYT.
It really is strikingly simple. DYT is designed as a direct drop-in replacement for ln or RMS norm. The math is just. DYTx equals a tan plus BOCO.
Okay, walk us through those parameters. We have the gamma and beta again.
Right. BOC and BOC are the learnable per-channel vectors, just like in regular normalization. They scale and shift the output, providing that final flexibility.
But the new part is OCA, alpha.
Oh, and the tan.
Exactly. OCA is a learnable scalar. This is the dynamic part. It learns to scale the input x before it goes into the tan. This allows the tan function to adapt its steepness, essentially mimicking how ln seem to operate on different scales depending on the input range, like we saw in figure 2. And 10 provides that core squashing nonlinearity we identify as crucial.
And crucially, this operates element-wise. Absolutely crucial distinction. DYT is purely element-wise. It applies, quote, 10x plus B2 to each number in the input tensor independently. It does not compute any means, variances, or any other statistics. No aggregation across dimensions. That's core to its simplicity.
And figure 1 shows it just slots right in where the ln used to be in a transformer block.
Seamlessly.
Yeah.
You just replace the ln or RMS norm layer with a dy2 layer. It applies inattention blocks, FFNs, the final normalization step, wherever you had the original normalization. And just to be crystal clear, DYT replaces the normalization layer. It's not a new activation function. You still keep your GELU or ReLU or whatever activation you're using elsewhere in the block.
Right. It's a direct swap for the normalization component only.
Exactly. And a big plus they mention is that often you don't even need to retune your training hyperparameters much. It tends to work well with the settings optimized for the original normalized model.
What about initializing these new parameters, especially alpha?
Good question. The OC and OC are initialized just like in LNRMS norm gamma to 1s, beta to 0s, standard practice. For OC, the default initialization is just 0.5. And the paper finds this works well across most models and tasks. The main exception, which we'll get to, is LLMs, where tuning up becomes more important. But for many cases, 0.5 is robust.
So to recap the definition,
Yeah.
It's not technically normalization because it doesn't compute stats.
Correct. No stats, no aggregation, purely element-wise.
But functionally, it preserves the key effect of normalization, that nonlinear squashing of extreme values, while keeping the central part mostly linear by using that learnable tanh-like.
That's the core trick. It mimics the essential behavior observed empirically, but achieves it through a much simpler, direct function. It captures the S-shape without needing the statistics.
Okay, the concept is elegant, the mechanism seems plausible based on their analysis, but the real test is performance, right, across the board.
Absolutely. And they were rigorous here. The protocol was consistent. Take an existing architecture, replace LN or RMS norm with DYT, and then train and test using the exact same official protocols. Same data, optimizers, schedule.
Apples to apples comparison.
Exactly. And importantly, as we mentioned, for most experiments, they used identical hyperparameters to the normalized baselines. This really highlights how easy DYT is to adopt in practice. Appendix B notes a few minor tunings, but generally it just works.
So let's talk results. Supervised vision first, VIT and con next.
Right. VT base, VT large, COM-next base, COM-next large, all on ImageNet 1K. Table 1 shows the results. And DYT achieves performance that's slightly better or very similar. For instance, VITL gets 83.6% top 1 accuracy with DYT compared to 83.1% with LN. That's a 0.5% bump. COM-next TL is 84.4%. Yes, 84.3%. A tiny bit better. So it's definitely competitive, maybe even slightly advantageous with the simpler layer.
And the training itself looks stable.
Yeah, figure 5 shows the training loss curves. DYT and LN models track each other very closely. Suggests similar learning dynamics, stable convergence, no red flags there.
Okay, what about self-supervised learning? MAE and DINO.
Tested both using VIT backbones on ImageNet. Table 2 has these results. Again, DYT performs consistently on par. MAE, VITB, identical 83.2% accuracy for both. DINO VITB with patch size 8. DYT actually edged slightly ahead, 84.5%, V is 84.1%. So it holds up really well in the self-supervised setting too.
Impressive consistency. How about diffusion models for image generation, DIT?
They tested DIT base, large, and XL on ImageNet. One detail. In DIT, the LN affine parameters are used for class conditioning. They kept that conditioning mechanism intact and only replaced the core X part with tanh-like, a careful substitution.
Makes sense. And the metric is FID, lower is better.
Right. Table 3 shows DYT gets comparable or even improved FID scores. DITB, for example, dropped from 64.9 FID with LN to 63.9 with DYT. Lower is better, so that's an improvement. DDIT-XL had a tiny uptick in FID, 20.8 for DYP versus 19.9 for LN, but still very much in the same ballpark. So again, highly competitive performance in generative models.
All right, the big one, large language models, LMA, right, replacing RMS norm.
Exactly. They trained LaMA7B, 13B, 34B, and 70B on the pile, comparing DYT against the default RMS norm. Now here, they did need one specific modification for DYT, adding a learnable scalar right after the initial embedding layer, initialized to squirt embedding dim.
Why was that needed?
They found that without it, activations at the very start of training were too small, which destabilized things. This initial scalar boost fixed it. It's actually similar to a fixed scalar used in the original transformer paper.
Okay, a small tweak for stability.
Yeah.
And the evaluation.
Training loss plus average performance on 15 zero-shot tasks from Elm Evil following the OpenLlama protocol. And the results in Table 4 are, well, basically identical. DYT performs on par with RMS norm across all model sizes and tasks, LaMA70B, for example. Same average score, 0.549. Same training loss, 1.45 for both DYT and RMS norm.
Wow. No drop-off even at that scale.
None. And figure 6 shows the loss curves are practically overlapping for billions of tokens. Same training trends, same final performance.
Incredible. Did they test anything else? Speech, DNA?
They did. For speech, Wave 2vec 2.0 on LibreSpeech. They kept the very first group norm layer, which handles raw audio input normalization, but replaced all internal transformer LNs with DYT. Table 5 shows comparable validation loss, basically the same performance. And for DNA sequence modeling, they tested hyena DNA and caduceus on genomic benchmarks. Table 6 again shows DYT is comparable to LN, achieving identical accuracies.
Man, that is incredibly consistent. Vision, language, generation, speech, DNA, supervised, self-supervised, small models, huge models. DYT just seems to work across the board.
The breadth of validation is really one of the paper's major strengths. It strongly suggests DYT isn't just some niche trick, but a genuinely general-purpose alternative.
Okay, so it works, but why does it work so well? The paper dives into ablation studies to pick apart DYT itself, right? Looking at the tan and that parameter.
Exactly. Ablations are key to understanding mechanism. First, they played with the tan function. What if you replace it? They tried hard tan and sigmoid, other squashing functions, and critically, they tried replacing tan with just an identity function. So, Ganex plus Barentz, no squashing at all.
What happened without the squashing?
Training completely failed. Table 7 shows this clearly. Using the identity function led to instability and divergence. VITB, for instance, just crashed after reaching about 61% accuracy, way below the usual 82%. But using tan, hard tan, or sigmoid all allowed stable training and gave decent results. So the non-linear squashing is absolutely essential.
And tan was the best among them.
Yes. Tan consistently gave the best performance, maybe, as they suggest, due to its smoothness and being zero-centered, which often helps optimization. Figure 7 visualizes these different functions.
Okay, squashing is crucial. What about removing the learnable arc? Just using tan X?
They tested that too, keeping the squashing but fixing arc effectively to 1 or removing it. Table 8 shows the results, removing arc performance across the board. For VITB with 10, accuracy dropped from 82.5% with I down to 81.1% without it. Similar drops for hard tan and sigmoid. So I isn't just for show. That learnable scaling factor is critical for achieving top performance. The dynamic aspect matters.
This alpha parameter really seems key then. What did they find out about how it behaves during training? What's it actually learning to do?
It's doing something quite interesting. Figure 8, the left panel, tracks arc and the inverse standard deviation first beat of the layer's input activations during training. And what you see is that arc closely tracks first state. They fluctuate together. If the activation standard deviation goes up, first state goes down, and R tends to go down too, and vice versa.
So alpha is learning to kind of normalize the scale before the tan.
It's partially functioning like a normalization factor, yes. It's learning a value that's related to the inverse scale of the overall input activations to that layer. But, and this is important, unlike LAN, which normalizes per token using that token's specific XD deviation, LA applies one single scaling factor to all activations going into the tan. So LA helps control the overall scale, contributing to stability, but it cannot perform the nonlinear squashing of outliers by itself. That's still the job of the tan. It needs both components.
Got it. And after training, does this relationship hold?
Yes. The right panel of figure 8 shows a strong correlation between the final learned I values and the first test of activations in the trained model. Layers with higher activation SDDev, lower first DE, tend to learn smaller APA values. They also note that deeper layers tend to have larger activation standard deviations, which is a known characteristic of deep residual nets, and ALIA adapts accordingly.
Okay, so DYT seems internally consistent. How does it stack up against other ways people have tried to train networks without normalization, like fix-up or skipping it?
Good question. They did compare DYT against several existing normalization-free methods. Broadly, you have 1. Initialization-based methods like fix-up and skipping it. These focus on careful weight initialization, often scaling things down, to prevent activations gradients from exploding early on. 2. Weight normalization-based methods like Shreparam. These impose constraints or reparameterize weights during training to maintain stability.
So different philosophies for achieving stability without explicit normalization layers.
Right. The paper compared DYT to fix-up, skip-it, and Shreparam on VIT tasks, ImageNet classification, and MAE. Crucially, for a fair fight, they did a learning rate search for all methods because methods like fix-up often need much lower LRs. So these results might differ slightly from the earlier ones where DYT used default LRs.
Apples to apples comparison with optimized LRs for everyone. What was the outcome?
Table 9 shows DYT consistently outperforms the others. For VITB classification, LN baseline was 82.3%, DYT got 82.8%, but FIXUP only reached 77.2%, skipping at 74.1%. Shrep-RAM did well at 82.5%, but DYT was still slightly better. Similar story for VITL and the MAE tasks. DYT just came out ahead of the other normalization-free approaches they tested.
We touched on alpha initialization earlier, saying Bind 5 was generally okay except maybe for LLMs. Can we revisit that? How sensitive are non-LLM models to that initial alpha value?
And generally not very sensitive. Figure 9 shows performance across a range of bound values, from 0.5 up to 1.2 usually for tasks like ImageNet classification and MAE. Performance is pretty stable in that range. The main effect of changing arrows seems to be in the very early training dynamics.
But there was an exception.
Yes, for larger models or higher learning rates. Supervised VITL, for example, could diverge if IDA was set above 0.6 with the standard LR. They needed to reduce the LR for stability with higher. Figure 10 shows this. So the general rule seems to be bigger model or higher LR might need a smaller initial IDFL for stability. The default of bet 05 is a safe bet that balances stability and performance for most non-LLM cases.
Okay, that makes sense for standard models. But then we get to LLMs, where you said initialization is much more critical. What specific tuning helps there?
Right. For LLMs, tuning to makes a substantial difference. It's not just about stability. It can really impact final performance. They did extensive llama pre-training runs just to find the optimal M. Two key findings emerge, shown in Table 10. First, larger models need smaller LO values. For Llama 7B, the best was around 0.8 for attention blocks and 0.2 for other blocks. But for the huge Llama 70B, it dropped to 0.2 for attention and just 0.05 for others.
Wow, quite a difference based on scale.
A huge difference. The second finding was that attention blocks benefit from higher ZIR compared to FFN blocks or the final DYT layer. Figure 11 shows this with heat maps. You get the best lowest training loss when IR for attention is relatively high and IR for other blocks is relatively low. There's a clear optimal zone.
So it's not just one IR for the whole model, but different optimal values for different block types. And it depends heavily on model size.
Precisely. And they dug a bit deeper. Is it model width or depth that drives the sensitivity? Table 11 makes it clear. Width is the primary factor. As networks get wider, the optimal EO values consistently decrease, especially for the non-attention blocks. Depth didn't seem to matter nearly as much.
Any hypothesis why width is so critical?
The paper suggests it might be related to just how excessively wide LLMs are compared to other models. Maybe something about the dynamics in very wide layers makes them more sensitive to the initial scaling provided by IR.
Okay, so DYT is powerful, versatile, but requires some care with initialization in LLMs. Like any method, it must have limits. What did the paper identify as current limitations?
They were transparent about two main ones. First, incompatibility with batch normalization. All the successes were replacing LN or RMS norm, common in transformers, but when they tried replacing BN in classic convnets like ResNet 50 or VGG19, it didn't go well. Table 16 in the appendix shows significant performance drops. ResNet 50 accuracy fell from 76.2% with BN to 68.9% with DYT. VGG19 dropped from 72.7% to 71.0%.
Any idea why it struggles with BN architectures?
Their hypothesis is related to density. BN layers often appear much more frequently in convnets, like after almost every convolutional layer. LN in transformers is usually less frequent, maybe once per block. This difference in placement and frequency, plus maybe how BN interacts with convolutional features, might be why DYT doesn't translate well currently. It needs more study.
Okay, so it's primarily a transformer replacement for now. What's the second limitation?
Computational efficiency, or rather, the lack of a significant speed-up in practice right now. Conceptually, DYT is simpler. Element-wise, TAN, no complex statistics, no reduction operation. You'd think it would be faster. And Table 14 shows that without compiler optimizations like torch.compile, DYT can be faster than RMS norm, especially the custom CUDA kernel for RMS norm.
But with optimizations.
With torch.compile, as shown in Table 15, the latency difference basically vanishes. Both DYT and optimized RMS norm end up being very fast and roughly equal in speed.
So no free lunch on speed just yet?
Not automatically, no. However, the paper rightly points out that DYT's architectural simplicity, the lack of reduction, might still offer optimization potential down the line. Maybe on specific hardware where reductions are costly, or through better fusion with preceding matrix multiplies in future compilers or custom kernels. The potential is there, even if not realized universally today.
All right, let's try and wrap this up. What we've really seen today is a fascinating challenge to something we almost took as gospel in deep learning. the necessity of normalization layers.
Mm.
This deep dive into transformers without normalization shows that Dynamic Tanh, DYT, offers this surprisingly elegant, simple, and yet really effective alternative.
Absolutely. By honing in on that empirical observation that normalization layers often end up performing a tan-like squashing of extreme values, they designed a function that mimics this key behavior directly. No complex statistics needed. And the results speak for themselves. Consistent, strong performance across vision, language, speech, DNA. It's incredibly versatile.
It really forces you to rethink what normalization is actually doing, doesn't it? Maybe the complex statistics were, in some sense, just an emergent way to achieve this simpler squashing effect.
It certainly suggests that. And this work doesn't just give us a new tool, DYT, but it deepens our understanding of the existing tools, too. And the practical guidance on dynamics and initialization, especially the nuances for LLMs, is really valuable for anyone wanting to try this out. Yes, it has limitations. The BN incompatibility needs work, and the speed up isn't guaranteed yet, but its success in the huge domain of transformers is undeniable. It opens doors for simpler, potentially more efficient models.
So, for everyone listening, as you design and train the next wave of deep learning models, maybe normalization isn't quite the indispensable component we thought. Could DYT lead to simpler hardware, faster training in some contexts? It leaves us with a really provocative thought, I think. What other complex, essential parts of our current models might be hiding a simpler, more elegant core function, just waiting for us to uncover it?